Hey, here's a screencast for you, working through an optimization example. I'm calling it joint area constrained by perimeter. So here's the problem. A single piece of wire is 100 centimeters long. We want to cut it in one place and take the two pieces and shape one into an equilateral triangle and the other into a circle. Where do we cut the wire to get shapes whose total area is the least? That's the problem. When you read the problem again, you see this word least. That's a superlative, so that's an indicator that this is an optimization problem, and that's indeed what we want to do. What are we optimizing? Well, what is it that we want to find the minimum of? What is it that we're looking for to make the least? Well, it's the total area. So the function we're going to want to build is a function that gives us the total area of the two shapes. So that's the total area, well, not the total. That's the area of the triangle plus the area of the circle. So let's find expressions for each of these. The one that's probably most familiar to us is the area of a circle. So if I have a circle, and I know its radius, for example, I know the area is pi r squared. So I can use this formula for the area part. How about the area of an equilateral triangle? Well, if I have an equilateral triangle, here's my best attempt to sketch it. And if I say the side length is length L, so let's just, so we're not mistaking what L stands for. What's the area of the triangle? Well, I know the area of a triangle is 1/2 the base times the height. So if I were to drop a perpendicular here to get the height, what do I know about a perpendicular? Well, some basic geometry that hopefully you've seen. When you drop a perpendicular, it's perpendicular to the base. And in this case of an equilateral triangle, it bisects the base. So that means that this length right here is L over 2. And if I can find the height, then the product of this number and the height is going to be the area of my equilateral triangle. Now, this is the triangle I'm interested in here is a right triangle. I can find the other length using the Pythagorean theorem, and I'll let you check. But that length there is going to be the root 3 over 2 times L. So that area of my green triangle here is going to be 1/2 its base times its height. But the area of this whole thing is going to be 1/2 its base, i.e. this, times the height. So the area of the triangle I'm looking for here is L over 2 times root 3 over 2 L, or root 3 over 4 L squared. This tells me my total area function that I'm going to minimize looks like this. The problem, of course, here is that I've got two variables. This is a Calculus 1 class. We know how to optimize functions of one variable. Well, I need to rewrite one of these variables in terms of the other variable. And that's where I'm going to use this constraint that we're working with a single piece of wire. because we're working with a wire that's 100 centimeters long, that 100 centimeters needs to give me the perimeter of my circle and the perimeter of my triangle. Now the perimeter of my circle, I know that's its circumference. And so the circle has radius r, the circumference is 2 pi r. And the perimeter of my equilateral triangle, since it's got side length L, its perimeter is 3L. So here's my equation that relates R and L. I'm going to solve this for one variable, and that is writing it in terms of the other. And I'm going to choose to solve it for L. And you can check to see that this would give me L equals 1/3 of 100 minus 2 pi r. And with that, I can write my total area function as a function of a single variable. That's going to be root 3 over 4 times 1/3 100 minus 2 pi r. That's L, so that's squared. And then I have 2 pi r squared. And that's my area function. So this is the function I want to optimize. And we're going to use calculus to do it. So let's copy this to the next page. All right, what do we know about this function? Well, let's do it in the context of optimization. So our optimization says we want to find the minimum. In this case, we're going to think of global minimum, but it'll be interesting to see if we have a couple choices for that. But let's find the global minimum, and we know those occur at critical points. So let's catalog the critical points of this function. It's good to remind ourselves that critical points come in 3 flavors: endpoints, singular points, and stationary points. Looking at this function, you can see that it's a polynomial in R, so it's going to be differentiable everywhere. It's not going to have any singular points. So let's just get rid of singular points. Endpoints? Well, you look at this function and you think, well, what are the endpoints? As a function, this is defined everywhere, so there's no natural set of endpoints. Like endpoints, the domain of this is all real numbers. But when you think about the problem and the fact that we're taking a piece of wire and we're cutting it to give us our 2 perimeters, that tells you about R. What's the smallest R can be and what's the biggest R can be. When you think about it for a minute, the problem tells us that R is between 0, okay, and that's the case where all the wire goes to the triangle, because our circle has radius 0, and R can go to the other extreme where we have no wire for the triangle, and all the wire goes for the perimeter of the circle. So if our circumference is 100 centimeters, then our radius must be 100 over 2 pi. And we can write that as 5 or 50 over pi. And while we're here, let's take a second and figure out what that is. What's the decimal approximation of that? I'm typing this into my computer. That's approximately equal to 15.9. So these are going to be our 2 endpoints. R equals 0 and R equals 50 over pi, which is 15.9 approximately. So the other type of critical point we need to look for are the stationary points. So these are where the derivative is 0. So let's calculate the derivative and set it equals 0 and solve. Our functions at the top of this half of the page, so it's pretty easy matter to start computing. So what do we get? We get root 3 over 4 times 2 times, here we're going to use a chain rule. In fact, we're going to, well, taking the derivative of the inside of this function, you'll see you've got 1/3 times the derivative of this thing, and the derivative of this thing is minus 2 pi. So I get minus 2 pi over 3. And then the other term, the derivative is 2 pi. Oh, that seems pretty gross. That's all right. Let's just start simplifying it. We've got a 2 in the numerator, another 2 in the numerator here, and in the denominator we've got a 4. So those all cancel. We've got a 3 in the denominator here, and a 3 in the denominator here, and a square root of 3 up there. So these are going to combine to give me in the denominator a 3 root 3. And in my numerator, I'm going to have that minus pi. So I believe this is what I have, right? I took care of the 3's downstairs. That gives me that. And I have the pi upstairs. That gives me that. Yeah, those were taken care of in part of the 3's. Got that, good. Plus 2 pi r. Now what I want to do is I want to solve this. Well, not solve this. I want to isolate my r's. I want to multiply this out and group all my r's together. So I get minus 100 pi over 3 root 3 plus 2 pi squared r over 3 root 3 plus 2 pi r. So here I see I've got my terms with my r in it. I'm going to factor the r out of those. And that's what I sought to do. The next thing I want to do is, well, let's set this equal to 0. Because what we want, right, we want the stationary points. I've just computed or found an expression for my derivative, but now let's set it equal to 0. If we set it equal to 0, we get that. And I'm going to add that constant term to both sides. So I get the expression, or the equation, 100 pi over 3 root 3 equals, now here I want to write this as a single fraction. So I'm going to multiply this 2 pi by 3 root 3 over 3 root 3. And I get 2 pi squared plus 3 root 3 times 2 pi all over 3 root 3 r. With that done, I'm going to multiply both sides of this expression by the reciprocal of the number multiplying r, and that's going to give me r equals 3 root 3 over 2 pi squared plus 3 root 3 times 2 pi times 100 pi over 3 root 3. Now those 3 root 3's will cancel. What else is going to cancel? I've got a 2 in each term in my denominator here. I could factor that 2 out, and it would reduce my 100 to a 50. I've got a pi in each of those factors in my denominator, so I could factor out a pi, and that would cancel with that pi there. So this is a lot of stuff happening here. I'm left with a 50 upstairs, and downstairs I have a pi plus 3 root 3. All right, let me throw this into my computer and see what this is. And this is approximately equal to 5.996, so almost 6. But this is my stationary point, it looks like. Now I am ready to make a chart of sine, so let's start a new page and do that. So here's my r-axis. I'm going to put my endpoints on it. My endpoints were my endpoints were 0 and 100 over 2 pi. And that stationary point I just found, I'm going to call it r0. Because this is an awful lot to write, so just to abbreviate r0. And that's 50 over pi plus 3 square root of 3. Let's write that over here. So let's figure out what the sine of my derivative is. Well, I'm just going to pick some numbers. What did I say this was? This was approximately equal to 6. I'm going to pick some numbers that are on either side of my r0 and see what the sine of my derivative is. So in this case, I'm going to choose 10, right? Because what did I say 10 over 2 pi was? Here, 10 over 2 pi is 15. So 10 seems to be a nice round number to work with. And 1. So my 1 is down here and my 10 is up here. Okay, so let's go back and look at what my derivative formula is. My derivative is right here. So I'm going to plug 10 in. I'm going to use my computer and plug 10 in. So I get minus pi divided by 3 times the square root of 3. Sorry. Minus pi divided by 3 times the square root of 3. Times 100 minus 2 times pi times 1. I'm plugging in 1 plus 2 times pi times 1. So here I get a minus 50.4. Okay, so that's negative. So I'm going to put a negative there. That's not what I wanted to get. Plug in 10. Let's see what we get. I get 40. So that's positive. Now let's plug in some values. I'm going to calculate a prime of 1 and a prime of 10. Because 1 is a number in my interval that's to the left of r0, and 10 is a number in my interval to the right of r0. Plugging 1 into the formula for my derivative and 10 into the formula for my derivative. And to remind you, my formula for my derivative is right here. So if I plug in 1 for r, If I plug in 10 for r, you'll see what I get is at 1, I get approximately negative 50.4. So my derivative is negative there. If I plug in 10, my derivative is approximately 40.4. So that's a positive there. That tells me my function's going down to the left of r0 and up to the right of r0. So the first derivative test tells us r0 equals 50 over pi plus 3 root 3 is a global minimum for the total area function. And that means that what we do is that on my 100 centimeter piece of wire, I'm going to make a cut at approximately 5.99 centimeters from one end. And it's this part that I make into the circle, and it's this part that I make into the triangle. But this is what the problem was asking us for, and we use calculus to find it. One thing that I'll note is looking at our chart of sines here, and what the first derivative test is telling us, is that each of the endpoints is a global maximum. And it might be interesting to look at to see which one of these, or each of the endpoints is a local maximum, but it's interesting to see which one of these is the global maximum. And you can go and calculate what's the total area for 0 and what's the total area for 100 over 2 pi. That is, what's your total area if you don't include the circle, and what's the total area if you do include the circle. I'll stop there. You can play with this some more. Classic optimization problem.